This is the Smart Trail Camera group consisting of Bobby, Tate, Rio, Alyson, and mentors Dr. Go. What is the need for a Smart Trail Cam? Some of the current issues and limitations from the market on cellular cameras is that you have to pay a cellular plan in order to use it each month, and you need cell service in order to send images from the trail camera to your phone. This means that some remote locations can't be reached by cellular trail cameras. The Smart Trail Camera aims to fix this by using radio, Bluetooth communication in order to send images from the trail cam to your device. A Smart Trail Camera consists of 3 different nodes. On the edge device or your trail cam, when an animal walks in front of the motion sensor, the camera is triggered, which sends the image from the camera to the AI module on the device. This provides classification and a confidence score on what animal it thinks it is, and then sends that image from the edge device to the secondary device called the mother node. The mother node then sends the image using Bluetooth and Bluetooth Low Energy to the app. On the app, you can view the image and also choose which animals you'd like to see. As for the hardware, on the edge device, you have a Huzzah 32 featherboard, an Adafruit LoRa module, a Grove AI Vision V2 module, a PIR motion sensor, and a Raspberry Pi camera. On the mother node, you just have the Huzzah 32 featherboard and the LoRa module. A custom PCB was created in KiCad in order to house all of our components, which was then manufactured by Oshpark. After manufacturing, all components were then soldered to the PCB and then housed in a custom enclosure. The custom enclosure was modeled in FreeCAD and then printed by the UAH Makerspace.
For the cybersecurity component of our project, we were to develop a threat model using the STRIVE framework and 2 cyber attacks and defenses of the system. So taking a look here at the image, we have our assets, which are to the left of the dash line, and we have the user, which is to the right. The dotted line here, or the dash line here, represents our trust boundary. And based on the curve of this trust boundary, we're saying that we trust our assets to the left of it more than we trust our user input. And then as for the cyber attacks, we came up with 2. One is a persistent login, and the other being a Bluetooth man in the middle. The weakness for the persistent login is that we had a flag in our code for login, and it's called isLoggedIn. And when that flag is set to true, then the user is logged into the app without any further checks. So to mitigate that, we could use an encrypted shared purposes, or we could validate user credentials with every app launch. And as for the man in the middle, the way our app was set up was that we implicitly trust the Bluetooth devices. And a way to mitigate that would be to limit the devices to a whitelist or use a type of authentication for when pairing Bluetooth.
So this is our mobile application. When a user opens the app, they will see the view on the left where they are prompted to enter their email and password. If the user has not signed up to use the app, then they can click the sign up button and they'll be directed to this page on the right. Once they've put in an email and password, then they'll be able to use the app. So this page is where users will be able to see any recent images that were captured from their cameras in this image box here. The user is able to select which camera they want to see images from, and the camera that is selected will show up right here when they are connected. So users can also save images to their device if they want to. The view on the left is what the users will see if they're not connected to the mother node or any cameras, and the view on the right is what it will look like when a device has been connected. So as you can see, the device shows up right here, and it has been renamed, which is an option that the app offers users so they can keep track of which images are coming from which camera. So when the user selects camera settings over here, then they'll be taken to the following screen. So this screen shows what each camera that the user has. Again, the view on the left is when no devices are connected, and this one on the right shows a connected device. So from this page, the cameras can be renamed, and the user can set which animals they want to see from each individual camera. There's also a Reset Animals button that clears all the settings for all of the cameras. This back button takes you back to this main page, where there's also a disconnect button once the app is connected to the mother node, and a logout button that takes you back to this page.
Our goal is to create an offline, power-efficient camera system capable of detecting animals in remote environments. But performing this object detection at the edge on low-power, resource-constrained devices is a challenging and non-trivial task. But thanks to recent advancements in both hardware and algorithms, it's becoming increasingly feasible. On the hardware side, we now have access to efficient NPUs like the ARM Ethos G55, which we use in our project. It provides much-needed features of power efficiency, use of CNNs, and a powerful Vela compiler. While on the algorithmic side, we have state-of-the-art models such as YOLO, SSD, and TST, which offer high accuracy with lighter footprints. YOLO V8N features a modern anchor-free detection head and a lightweight architecture, making it ideal for embedded use. And so we've created a solution that combines these advancements into a portable smart trail camera. At its core is the Grove AI Vision V2, featuring the Ethos G55, which paired with the custom fine-tuned anti-quantized version of the YOLO V8N, achieves a strong balance of power and performance. And to further enhance detection, we use a technique called slice-aided hyperinference. While this does increase inference time, it significantly improves accuracy by processing smaller overlapping patches of an image, which is especially useful when detecting small or distant objects. What you see happening at 5x speed is the edge node sending data to the mother node, which aggregates a hypothetical bounding box in an image and then displays it, showcasing the full loop between the devices.